Okay, any other questions?
Sir, I don't get how the tunneling current is used to measure the depth.
Okay. So they have shown it horizontally because that's how their AFM was. But let's say this is my cantilever, the tip there. Can you see? Maybe you can, maybe you can come on. Actually, let me do it here. Okay, so this is my cantilever, let's say, with a diamond, whatever thing they attached, and you got the surface with, let's say, this atomic kind of corrugations, atomic roughness in a way, and there's a tunneling current that sort of flows back and I mean either depending on this bias between tip and sample, or the force is getting, so this cantilever will bend down if there is a force interaction. So what you do, you place another, doesn't have to be that much, another tip at the back of this. So as this bends, current will drop. If it goes back, the current will increase. So this is used as a tunneling tip between the back of the cantilever and the tip. And as this bends, so and they use gold, no? This was gold. So current is not a problem. Okay, any other questions? We have, I think we exceeded the 10 minutes discussion. Actually, I was over. Okay. Okay, good. So we spoke about how AFM was invented, first part, and how cantilevers should be of the dimensions, what they are. Okay. Now this one, about 15 minutes we'll spend in finding out or trying to know how the cantilever bending is detected. I said about 1 Newton per meter cantilever with a nanonewton force will bend by a nanometer displacement. Now typically bending is not in nanometers, right? Bending is an angle, right? You bends by an angle. So when I say bent by a nanometer, what I really mean is this idealized model where the cantilever is really thought of as a spring and the spring is getting stretched by a nanometer. So it is in a schematic way. You have a cantilever that, so this is bending of the cantilever, okay, and this is a straight cantilever. So when I say nanometer, this is what it is, and in a model way, this is basically, this is the cantilever with attached weight, let's say from there, and then it is sort of extended down by some amount, and that extension is what we call as a nanometer. But this is idealized as a spring, massless spring. The actual cantilever has angle theta, or you can call this as a if this is y and this is x, then you can call the slope there as dy by dx. Okay, that slope is what is actually is happens with the cantilever when it bends down with a force, right? So there are various ways in which you detect that bending. Okay, and in general people call this is few nanometers of bending, but bending is never in nanometers. If you want to convert that into angle, you just look at the length of the lever and how much this nanometer is, and you can divide this by that to get the angle, which is a very small angle. Okay, so that's one thing. Now before we go into the routine way of cantilevers bending detection, let's also look at some other other modes of detection, cantilevers bending detection. And the very first one was tunneling, of course. Tunneling is how is bending is measured, but that was too much of a problem because you got two junctions now. One is the tip and substrate junction, and then this cantilever on top of that is this another junction. And typically if you increase number of junctions, it will have a lot of drift issues, this issue, that issue, sometimes you will end up scanning or measuring the back of the cantilever instead of the thing below, right? Because you scan the whole thing. So it's all problematic. And very quickly, right after the first paper, the inventors of AFM themselves realized that that way of measuring cantilever's bending is not really a good idea. So the first bending method that was used, and if you really the first books on AFM, you see that list of technologies at the present time of that time which were used for measuring cantilever's bending. Uh, Quet from Stanford, who is also the co-inventor of AFM, he came up with something called piezoresistive cantilevers. Okay, the name is piezoresistive. And this thing is now coming back in, becoming quite popular for something called KPM, the Kelvin probe microscope. Okay, and it's coming back in vogue, this kind of piezoresistive, because it doesn't require any optics. It doesn't require any complicated optics. It's self-sensing in a way. What is the idea? The idea is borrowed from mechanical engineering. So if you really want to find out, if suppose you are in an earthquake prone area, you put the strain gauge elements in all parts of the building to see the building is under what kind of strain. Okay, if it is a ship, for instance, if you want to find out ship is out in the sea, and when it is subjected to all kind of stresses or forces, then various parts of this ship strain locally, and that it's not the whole thing is getting elongated as a ship, but locally they are causing some strains, and mechanical engineers use something called strain gauge device to measure that strain. So the idea is to have a gauge element which under strain will suddenly change its resistance, which means suppose you put that into a something called Wheatstone bridge, again 12th standard physics. Wheatstone bridge is 4 resistors, and if you apply some voltage and ground this, then there is a V1 and V2, that this 2, and if you balance this properly, this one equal, there is equation, Kirchhoff's equation. If you balance them properly, no voltage drop. You apply this voltage and you can balance so that V1 and V2 are same. Okay, and now suppose this is cantilever, but forget I put a strain gauge element in that particular circuit, and suddenly the strain is that element is under strain, and it changes the current, so it changes the resistance. That means a little bit of resistance change happens, and as a result you get a drop across these two. Now V1 is not equal to V2 anymore. It's just a small change in voltage that happens. Okay, and that's called strain gauge element, strain gauge. So what Quet did in Stanford is design a small strain gauge element at the cantilever's base. Okay, because the cantilever's base that comes under a lot of strain. If you look at the whole cantilever block, the strain happens large at the point where it is held, right? And this strain is not really linear kind, but it's the deformation, it's the angle. And if you put a strain gauge element, you have to design it and integrate it into this whole thing, and then put a Wheatstone bridge, and moment you bring the tip close to the sample, there will be a force that will repulsive force or attractive force, or you put hold that cantilever under some kind of load. This will cause a strain at the very base of the cantilever, and that strain is proportional to force. Okay, so that strain is proportional to bending. So still the question remains, how do you calibrate this, right? For instance, if this the current or the voltage drop between these two terminals, V1 minus V2, what drop corresponds to what bending, and then that bending through this equation, okay, Z, right? The G is bending. So how much is that? And then if you know the force constant, then you know the force. So if you finally want to measure the force, you measure the drop in voltage, convert that to cantilever's bending, and use the Hooke's law to from bending multiplied by the stiffness of the cantilever to get the amount of force that the cantilever has sensed. Okay. So, this means it requires a calibration procedure, what voltage corresponds to what force in the end. That we will come to later on, how this is done. So, this is one way of detecting cantilevers bending. The other one is called capacitive sensing, and this is not really in operation anymore, and people still ask why not. Strain gauge is coming back in a way. Right after AFM's invention, strain gauge was used quite a bit, and not used any with so much nowadays, but it's coming back in fashion. But this one is not happening. So, the idea here is that now you, with a resistor and a capacitor, so it's a RC network now. So, this is a cantilever surface, and you have a plate on top. So, you can, with the engineering technology that we talked about, right, you could create one layer that becomes a cantilever, and you can etch out the part in between, and the top part actually becomes another thing, but not floppy now, that's rigidly held with the top object, and this guy is a cantilever which bends down, and that changes the distance between the two. And we know that the capacitor of two plates, you change the distance, the capacitance changes, right. So, that means the voltage drop that is for a given amount of charge that is between the two, and what the dielectric is air in this case, you have moment the cantilever deflects, you get a signal. This I have not used myself, piezoresistive I have used, but this I have not used myself, but people say that it is very noisy, it picks up a lot of noise, maybe because of RC network or whatever the reason. You could also oscillate the cantilever, but that's besides the point. But that's what that's the another way of measuring cantilever's bending, is called capacitive sensor. Third one is interferometer, good old interferometry, because if you really think about small displacements, gravitational wave detection, extremely small displacement of one arm relative to another, right, to 10 to minus 21 in a meter. Okay. So, the strain values of gravitational wave detection are the thing perpendicular to each other, one expands more compared to another by 10 to minus 21 in a meter. So, so that there what we use interferometry, right, and we already know that from our BSc physics class and laboratory, that the small displacements are always sensed using interferometry. Okay, we'll not go into details, because these are the things which are not used so often. Fourth one, which came out little later, in maybe around 2000 or 2010, in that decade, and that's called tuning fork based detection. So, this is a different one, where what you do, I think this one is more appropriate. What you do, the tuning fork, right? The tuning forks are this kind of structures. The tuning fork that you use for tuning music things, which is also there in the watch, quartz crystal tuning forks. So, this is a kind of structure, and they have this electrical things. You provide electrical voltage, they will start oscillating the prongs, and this provides you a timekeeping element. You put a tip at one of these and hold this in a substrate, and this is called something called Q plus sensor, invented by people using ENSOM first initially, and then later someone called Gizibel, who really made this thing popular, and it's quite interesting one. So, now you have a tip here, and you hold this on a block, and you shake the block, and this also starts to shake, but you shake the block on resonance, this will have a more bending compared to the one that like you are shaking the thing, right, to smaller oscillations there and big there. So, small there and big there is what happens, and you could also excite it in a self sensing thing. The idea is, now what happens is that because of substrate which is closed there, if the tip comes into contact of substrate, this guy bends. This bending is differential. This bends more than that. That guy doesn't bend at all, and this guy bends a little bit. this creates a current through this too. Okay, and this is again using piezoelectricity to get the current. It's not piezoresistive, it's in a way it's a piezoresistive, because what you start to get current means the resistance has dropped or something. So this is one more thing that maybe you should keep in mind, the tuning fork based detection. Interferometer we talked about, and this is what you should pay close attention to. I think in 1988, right after piezoresistive cantilevers were used in AFM, group, I forgot, it's a paper in applied physics later, APL or Journal of Applied Physics. Have I mentioned it anywhere? No. Okay, no. Okay, so this is what you see. All AFMs, 99% of them that you see they use this technology for detecting the cantilever's bending, and this is why we should pay more attention to this. And the idea behind this is quite simple. What you do, you have a cantilever like that, substrate and scanner and everything. You got a laser that goes into a mirror. So, so that mirror sort of vertically brings the laser down. Okay, so this is horizontal. It will bring down this vertically. You always deliberately have about 12 degrees angle in the cantilever. And why is that? Can anyone say? You always have a, so the laser comes into the mirror and vertically goes down on a cantilever which is already at 12 degree angle to the horizontal. Without that detection, you always have to do this. Why? No, without even thinking about all, even piezoresistive one, you will have to have angle of 12 degrees or maybe whatever, 10, 20, whatever. 8 to 12, yeah. Anyone knows? Anyone can guess? Yeah? It has to? No, without, forget the detection. Any without the even piezoresistive one. Huh? No, no, no. Gravity is too low for force in this. This is a things are so close to each other. Van der Waals and electrostatic and electromagnetic interactions are much stronger than gravitational. Of course, gravitational is a long range thing. No, I'm saying nothing to do with detection scheme. Even then, you have to hold it like that. The reason is quite simple, and it is this. Suppose this is my substrate, and I bring my flat cantilever down, and my tip is only 10 microns jutting out. That means that I have to make sure that this guy has to be, it's very hard to make sure that it is parallelly coming down and only tip will interact. Any surface, if you two surfaces you are bringing them down, it's very difficult to make sure that the angles are, angle between them is 0. So you will always find that this surface is some angle with respect to the other. So to make sure that it's the cantilever that hits the surface first, because the surfaces, it's so hard to make the surfaces exactly parallel to each other to begin with. They will already have some angle or the other. But whatever angle they have, if you bring this down already to begin with, so you bent it by 10, 12 degrees. Okay. So all cantilever holders, everything will see, they will have small angle like that. Okay. So that the tip reaches the substrate first and not the bottom. If the bottom hits the surface first, then the tip will be hovering, hanging freely in the air, and it's not interacting with anything. So that's the very simple reason. This is not very complicated. So you always have this angle, so that this guy hits the substrate first and not the bottom. Okay, because this is only 100 microns, and over 100 micron, 1 degree angle you say between the two surfaces, and everything will go problematic. Okay, 1 degree angle towards the tip down is good, but 1 degree angle the other way around will create problems. You will never reach the surface. So this is already at an angle of 12 degrees. Now this guy goes there, hits, comes down to the cantilever, which is at angle. That means it will go back in other direction, which is convenient also, and we will take it to the detector. And this is a quadrant 4 sectional photodiode. Okay, how does this measure bending? So let's look at the detector. That's perfect sphere, a circle, sorry. I'm not too good at this. Okay, so this is section, that means this is 1, 2, let's say 3 and 4, and there is this insulating from each other. So light falls on any one of these will generate a current, right? You can put that into one small amplifier and this current will be converted to voltage proportional to the amount of light that is fallen on it. Okay, and these are photodiodes, which are basically silicon or germanium, whatever materials, semiconducting material, and these photodiodes essentially generate electron, light falls on it, generates electron hole pair. That efficiency decides how much for given microwatt of power, typically microamperes of current is generated. That's what, or microwatt of, I forgot, but that's the current typical efficiency that the current efficiency they have, quantum efficiency as they call it. Now this, suppose I have this laser comes and falls in one quadrant here, okay. The whole of laser is falling here. This means this one, let's call the voltage generated by this is V1. So only V1 will be whatever. Or suppose it falls in this, that's V2, and this V3, and this is V4. And each voltage signal corresponds to amount of light that is falling in that quadrant. Okay. Now if I have it fully here, everything else is 0, that's maximum. If I place it there, let's say in the middle, then V1 is equal to V2, or the power is distributed between these two, and these two are 0. If I make the spot fall exactly in the center, then V1, V2, V3 and V4 all equal. Okay. So what I can do with the help of this laser, which is mounted on a thing, or these two mirrors, what I can do is deflect this up and down before anything, the substitute all the way down. And if I shine this laser and focus in center by moving the detector up and down and sideways, and playing with this and playing with that, also playing with laser, that's the alignment procedure. We'll do this today in the lab. Okay. Doing all that, you put this guy in the center, the light that's coming from the cantilever. If you put in the center, all things are 0. So what is done? You add this top 2, sorry, and subtract it from V3 plus V4. And to normalize, if you want to normalize it, you can just total. So that means you add all of them together. Okay. All right. It is, maybe you can, this thing is coming in the way, maybe you can come on this side if you are having problem, those who are not able to see. Okay, so what does this give? You can forget the normalization, you can just, because then why do you divide by adding them all? Because the common noise gets cancelled, that's the idea. It's common mode rejection as we call in electronics. So addition of the top and subtract them from the bottom 2. Now if this is in center, this also is 0, but suppose this goes a little up, then this is large compared to this and you get a positive signal. This comes down, this is less compared to this, so this becomes negative. Okay. This is okay with everyone is fine with this. So now if the beam moves up and down, and this is exactly what is done for optical tweezers also, if you are ever happen to use it. So what happens is, if I have this thing going up and down, because the cantilever bending will move this beam up and down. So when the substrate is far away, the initial alignment procedure is that make this guy 0, and with the condition that the total signal of addition of all of this has to be large enough. What if my beam falls here or falls like this? That means what? I am getting some total thing, but it is not maximum. So two things: one, you maximize the total signal and make the addition of or the vertical signal, as this is called. This will be called the vertical signal. Okay, vertical signal. and this is made 0 with alignment with maximum voltage total thing added together. And now if I bring the sample close and the cantilever is bent down because of this, bringing the sample, or you hit the sample and cantilever is pushed down, then this will become positive, and you know that now the cantilever is bent from its non-bent position or equilibrium position. And then now the question is, how do I, once again the same calibration procedure, if I push the cantilever up by whatever force, whatever distance, how so that there is a bending in the cantilever happening, and you will say, okay, if I get 1 volt signal, then I push by that much. So you have to independently know how much you push by, how many nanometers you push by the. So suppose this guy is pushed up, this is put into contact, and this guy is pushed up by a nanometer. This bending will be, the moment of the end of the cantilever will move up by a nanometer, and since you know you moved the piezoelectric scanner by a nanometer, you can calibrate that nanometer to whatever volts. So that's also for each alignment. When you do, your laser power may go down, up, your cantilever reflects coating could be of a different type. You may have whatever laser power that's coming on the cantilever, maybe only 80% reflects back, or 70, depending on if the reflex coating has gone bad. So all of that put together, your calibration changes every time you are doing AFM experiment. Every time you do the alignment, it changes. So the first thing to do after doing alignment is to calibrate once again, and that there is a procedure in AFM which does this. The problems with that procedure, we'll talk about it in a tutorial session and other discussion parts. Okay, so everyone is okay with this vertical bending of the cantilever? Yeah, down.
How is vertical signal? How is vertical signal changing when the spot is moving above, like is in the middle, like is in first and second? Okay, but so my whether vertical signal will change when the spot is moving in the horizontal direction, like between 1 and 2 vertically. So the spot is moving up. Yeah. Uh, so the spot is between the detector 1 and 2 only, and the yeah, the intensity has not changed. The vertical signal will not change. Yeah. Yeah. Okay.
For do a friction loop, I load a cantilever with certain force, and I go laterally. And what will happen, because the cantilever is now pinned down with a friction force, this will do a torque. Four and subtract from V2 plus V3. So this will give you the torsion in the cantilever. Now the torsion force constant is different than the normal force constant, right? Cantilever spring constant different this way and different this way, and also the calibration of now torsional constant is even trickier issue. Normal, at least we have something or the other, but that's another topic. Okay. Yeah. Any other doubt? Okay, so this also we'll see today. Huh? Yes. Our JPK is cantilever signal, no? Or displacement, cantilever displacement, or cantilever Z, or all the many names. But that's from this thing is proportional to cantilever bending all the time. And the piezoelectric scanner below is one that will give you for image you have to scan. So you can either scan the tip along with that whole assembly, top assembly, its laser, detector and quadrant. That can be scanned and substrate can be kept as it is, or you can scan the substrate and keep everything fixed. So either way, the tip scanning and substrate scanning AFMs.
So during a normal scan, the laser is typically on all four quadrants, like, or it's in one quadrant only. Yes.
1 1. No, 1. This is one you get this in market as and this was available 25 years ago when I first built my AFM. I bought this from the market, and this circuit around it was built to get all this addition, subtraction, whatever. And after that, it just added subtractors, op amps, simple. For electronics, it's quite straightforward thing. Any other question for detection scheme? Yeah. Typically, it's IR. So few considerations are cantilever's reflex coating is normally aluminum, sometimes gold, and if you use red laser, there's absorption of these light into the material. Metals particularly are, I mean, the reason they are shiny because the visible light is reflected. The same logic works for metal, golds. Visible light is not used. Use IR laser to shine on the back. Yeah, many times. But red is also fine. In my PhD I used red because IR was expensive. Red was maybe 1,000 rupees in market, like the pointers, no, like that. Yeah. Yes, I mean the IR will cause some heating, but it is minimal. It's not that much, and this is a point of concern. And if you are a referee to a paper, you will raise such questions in a way. Yes, but then one should work out, see what is the power of laser that you're using. If it is like 50 milliwatt laser, yes, this will be problem. This will be a laser of extremely low intensity. Okay. It's mostly well, coating is used in such a way a lot of the power reflects, but some light falls off the cantilever. So you sort of focusing everything there, but many times it's hard to focus 50 microns. No, the width of the cantilever is 50 microns. So sometimes it falls off. That may heat up your sample a bit. So if your experiment is temperature sensitive, or you're claiming, let's say in biology you are claiming some reaction whatever, and you are using AFM to do this, reviewers will ask this question, that if you are using IR, maybe a careful reviewer maybe will ask such question. So you have to then say what is the amount of heat it will produce. You have to argue out it's negligibly small or whatever for the whole consideration. As I said, we can do either way.
But when we were moving that cantilever and tip,
Yeah.
so that laser and this four-sectional diode, those
Huh.
also need to be moved.
Okay,
When
so
the laser is
so you align everything, let the whole thing interact, cause something, and you can move this sideways like that, and also up and down this section. That's one way of doing it for imaging. The second way of doing is just keep this as it is, and this and this mount on something called flexure scanners nowadays. Okay, that is not, it's based on piezo, but it's different from piezo tubes. And those flexure scanners, actually that entire thing on the top, the whole detection assembly is moved. It's mounted on the flexure scanner. There's a possibility of. And our AFM is actually like that. The whole thing moves on the top. Yeah. Yes. Profiling of laser beam profiling. Good question. I think many times the laser comes with modes. Yeah. So this is where the problem comes, that the side modes will fall and the central one will be there. Sometimes the mode is elliptical. So if this thing goes back here, it will be elliptical. So if it is an angle, all problems. Yeah. So ideally, the real players in AFM technology will try to shape the beam and get it even smaller than the cantilever size on the top. But commercial AFMs, particularly diode lasers, this problem is quite a bit. Quite a bit. If you have a gas lasers and other lasers, the modes are not that problematic. But diode lasers already have a little bit of, asymmetry in the beam. Uh, People who make AFM sell them, sell you for couple of crores, so they do some technology to do it nowadays. Yeah.
For example, if someone is trying out
Yeah.
something of his own,
Then you better take care of this. But commercial AFMs, they do shaping of the beam to as much as they can. Particularly nowadays, the AFM, all the new AFM that you will try end up buying will have some kind of nice beam shaping.
other
The
than
beam,
laser, can there be some other sources,
like
for example, LEDs,
uh,
a little bit of optics?
yeah, can be used, but the problem with them, lasers are nice because one thing, they're coherent. They have to travel a distance from laser all the way to detector, about 10 millimeters. So if you use LED, they will spread, and by the time they reach the detector, from the reflected everything, I mean the cross section of detector is small, so lot of power will go. One thing, the coherent and collimated, no, the laser, the nice thing about laser is it will retain the power in that whatever the thing is. LED and all will spread out, so you can use in principle. The whole thing, I don't know if when we were BSc students, we used to have something called ballistic galvanometer in our, which was measuring tiny amounts of currents, and the way it worked was, there was a wire, and on which there will be some mirror stuck, and there will be a light, a lamp, basically not even laser, a lamp will come and go into wall, and farther it goes, more it will be, so we used to have a lamp there, and this light will go on to a wall, and as the wire has a torsion because of the current through the galvanometers, the current will produce a torsion, and the mirror was basically measuring that torsion in a far away. This is essentially the same thing, but you can't use lamp now because you have to put the light on something as tiny as 50 microns, and the lamp will just reduce the power. So yeah, laser is more convenient. Any other question? Okay, if not, then what is the time? 11:28 already. We have tea break at 11:30, right? Okay. So we've been discussing and talking. So this is at the break. Probably my plan was to finish it and then break, but it's okay. Uh,
Sir, can I ask, like, why interferometer based AFMs are not being used? Like, oh, they are prevalent.
This is the best thing to do. Now the company Asylum Research, which is Oxford Instrument, they now sell their interferometer AFM. It is now used. It is there.
As good as
Advantages and disadvantages. We are doing this for the advantages that the kind of problems we are working in our lab, we require interferometer. We build it and we have series of modifications in it. Our main focus is interferometer AFM actually. Yeah. Yeah.
Can this be coupled with the interferometric, the microscope also, for example, Moiri fluids and all?
Right. Yes, some people trying to do this to use interferometer to get the deflection itself. So for as you can now scan very fast this laser beam, so you don't use anything, you use this I mean the cantilever is there and substrate is far below, like a 10 micron or so at the tip, and use the light for so you can couple normal optical scanning microscope which is done with laser only for getting like this. They do know they shine the laser all over and get the sort of a map of this room. So that kind of thing people have now tried and it's there. Yeah. Happening now. Yeah. Yeah. Oh, beam shaping. That's another topic. So if you go to a laser lab that uses laser quite often, they do variety of things to do their beam shaping. And I don't know what all they do, but it is sometimes USP of certain labs. But it is done when for confocal microscopes or 2-photon or multi-photon, all of that, that is really a significant problem. And this is the knack of doing it is with laser industry. Toptica and the big laser companies, they do this all. If you start doing it in your lab, it's really, I think, something that is quite hard to do. So a laser, when you buy it, the industry takes care of it. Expensive lasers have quite well established Gaussian beam profile. Intensity also will fall in a Gaussian way. The profile will be circular. All of that. And some Japanese researchers use their lasers, which is standalone, independent, with nice beam to get focus it on only on the cantilever's back, not falling anywhere. You can do that. Fukuma's lab, I think, and also couple of labs in Japan, they do that. Yeah, the whole thing will be archived. All lectures will be on a Google Drive, and it will be on Gyan portal, and you will of course have access to it. No, everything will be there. Or what I can do, put my presentation on a Google Drive, share with you all. Huh. Yeah. Atomic force microscope paper. You can get it then from, once you know the reference, you can download it. It's there. We will try and see when you are around here. Maybe, Manmat, can you just download this atomic force microscope paper from 86? If it is downloadable, let's take some prints and keep it here, or the PDF can be shared with everyone. Yeah. That paper is quite good to see here. There are many papers now. And okay, so in the tea break and all, you come have a look at these books, not like read them, but have a look in the sense that these are the books which are relevant for biology, AFM in biology. So, and also tomorrow when Peter will start, Sabyasachi will also start. Some of these will be useful. I've got all this tag from